9.2 Series and Convergence. An infinite series is defined as the summation of a sequence with an infinite number of terms. That is, if the sequence a sub m is an infinite sequence, then the infinite series is defined as the summation from n equals 1 to infinity of a sub n. So that would be a sub 1 plus a sub 2 plus a sub 3 plus dot 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 plus a sub n plus dot dot dot. So a series is the summation of a sequence, because we talk about sequences and series together quite often. But the series would be the summation of a sequence. So we will find that when a sequence of partial sums converges, then the series will also converge. This lesson begins with a look at geometric series and telescoping series. The next lesson will explore p-series and harmonic series. Infinite sums are called series. We want to investigate limits of sequences of numbers. So you can see here that here's an example of a series, the summation from n equals 1 to infinity of 1 over 2 to the n, and we would just put n equals 1 in and we'd get 1/2. And then plus, when n equals 2, we get 1/4, plus when n equals 3, we get 1/8, plus dot dot dot, plus our 1 over 2 to the n. A sequence would be something where you're just listing values. Notice that there's no plus sign in between them. It's just a list of numbers. The value of a series is the limit of a sequence. So if I wanted to look at the summation from n equals 1 to infinity of 1 over 2 to the n, it would be equivalent to the limit of 2 to the n minus 1 over 2 to the n. Notice that in the series, that 1/2 plus 1/4 gives us that 3/4. That 1/2 plus 1/4 plus 1/8 gives us our 7/8. Okay, so that's the connection between those. Sorry about that. Okay. All right. So now, example number 1. Write the indicated partial sum S sub n for the series summation n equals 1 to n of 1 over 2 to the n minus 1. They want us to find S sub 1. So that is the partial sum of just the term when n is 1. So this is just going to be 1 over 2 to the 1 minus 1. So 1 over 2 to the 0, 1 over 1, 1. It's just that one term. S sub 2 would be the 1 over 2 to the 1 minus 1 plus 1 over 2 to the 2 minus 1. You'd add up the first two terms because it's sub 2. So we said that one was 1 plus 1/2. That's going to give us 3/2. S sub 3 is the partial sum of the first three terms. So we've got our first term, 1 over 2 to the 1 minus 1, plus 1 over 2 to the 2 minus 1, plus 1 over 2 to the 3 minus 1. So we said this was 1. The second one is 1/2. The third one is 1/4. So if we added those together, actually, I'm just going to leave it like that. We really didn't even need, we kind of want to a lot of times look at it. If you wanted to add these, what would it be? 4, 5, 6, 7 fourths if we added them. And S sub n would just be basically adding, you know, the 1 plus the 1/2 plus the 1/4 plus dot 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 plus, and then you'd have your last one would be your nth one. So that is what S sub n would look like. Okay. So now for the infinite series, summation n equals 1 to infinity a sub n, the nth partial sum is given by S sub n, which is just your first term plus your second term plus your third term plus dot, 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 all the way up to your nth term. If the sequence of partial sums, S sub n, converges to S, then the series converges. The limit S is called the sum of the series. If the sequence of summation n diverges, then the series diverges. So that leads us to looking at the geometric series. So a geometric series is summation from n equals 0 to infinity, a times r to the n, which would be your a, because that would be r to the 0, and then plus a times r to the 1, plus a times r to the 2, dot, 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 as long as a does not equal 0. You could also start with n equals 1, and then you would have to adjust your first term, or adjust your r to the power, because you want that first term to be r to the 0, okay? So either way, with n equals 0 or n equals 1, it just depends on, and you'll see it different ways. Convergence of a geometric series. A geometric series with ratio r diverges if the absolute value of r is greater than or equal to 1. If the absolute value of r lies between 0 and 1, then the series converges to the sum a over 1 minus r. So you do have to remember this. That's the sum of a geometric series that converges. So, if you've determined what your r is and you've determined that it's between 0 and 1, then you can find the sum. So now, partial sum of a geometric series, S sub n. So to find S sub n, you're going to take your first term minus your nth term times r over 1 minus r. So the first term times 1 minus r to the n over 1 minus r is another way to write that. So we're going to consider the infinite geometric series a sub n equals 8 plus 8 fifths plus 8 25ths plus 8 over 125 plus dot, 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 dot. So find a sub 1. Well, that is easy. It's just your first term. What is r? Well, notice that if I was trying to figure out what this was, if our first term is 8 times, this seems to be 1/5 to the, and what would you think if this is our first term? Wouldn't this have to be n minus 1? Because for my a sub 1, this 1/5 did not show. So therefore, this would be your a sub n. So your r then is 1/5. Because on the second term, it would be 8 fifths. On the third term, it's going to be 8 over 25. And so writing the explicit rule is something that I just did, only I want to show it with a summation. So we've got our summation, n equals 1 to infinity, 8 times 1/5, to the n minus 1. Sorry about that, my pen is being weird. Try that again. Okay. And so that would be our explicit rule. We could find any a sub n that we wanted to there. Just if I wanted a sub 100, I could find it. That's explicit. find the fourth partial sum, S sub 4. So our fourth partial sum is just going to be 8 plus 8 fifths plus 8 25ths plus 8 1/25. That would be your S sub 4. And if you added those up on your calculator, you would get 1248 over 125. And then find the infinite sum, S sub n. Well, if you want the infinite sum, we had to make sure that our r was between 0 and 1, and it is. It's 1/5. And so that's going to be our a over 1 minus r. And a is our first term. 8 over 1 minus 1/5 would be 8 divided by 4/5, which would be 40/4, 10. F, find the limit as n goes to infinity, S sub n. So the limit as n goes to infinity, our S sub n, I'm going to write it as 8 over 5 to the n minus 1. And when you look at it like that, if you put infinity into that denominator and this numerator stays 8, this is going to go to 0. Okay, so that's what happens to your limit. So it does have a finite value, so it's going to converge. Find each of the following, if possible. If not possible, explain why. Okay, so for this one, it's the summation from n equals 0 to infinity, and of 2 times 1 over 3 to the n, plus summation from n equals 1 to infinity, 2 to the n minus 1 over 5 to the n. So when I look at this first one, what you want to imagine is there a way that this could be geometric? Okay? So if I rewrote this as 2 times 1/3 to the n, would that still be right? Yes, and since it goes from n equals 0 to infinity, I can just have an n there. So if you want to look back up here and remind yourself of this one, where did we define it like that? Sorry about that. Oh, no, it's right here. Okay, so remember, for this one, if it can be just a times r to the n if n is 0. And we did have n equals 0. So this is the definition of a geometric series. Since the r, this is my r right here, since the r is between 0 and 1, I know that my sum, so this whole thing right here, is a over 1 minus r. Well, my a would be 2, because that would be my first term, over 1 minus 1/3. So it's almost like you just have to look at it and decide, what do I know about, about this summation? What kind is it? What can I use? What do I know about it? Now, let's look at the second one. The second one, summation n equals 1 to infinity. So what I want to do is somehow write this so that my r is to the n minus 1. So when I look at this, I'm like, okay, well, I've got 2 to the n minus 1, right? And I could look at this as 5 times 5 to the n minus 1. Because if this was 5 to the 1 and that was 5 to the n minus 1, and I'm multiplying, I can add those exponents, and then I would get 5 to the n again. But if I write it like that, then I can see that this would become 1/5 times 2/5 to the n minus 1, which is in the format that we talked about up here, the second format, okay? So that your R, that second format gives you your R to be this guy to the n minus 1. And your A sub 1 is going to be 1/5. But again, since 2/5 is between 0 and 1, you can say that that is a geometric series, and you can use your first term over 1 minus R as your summation. So sometimes you have to mess around with it a little bit to make it into something that you can use. So what was this? This was 2 over 2/3 plus 1/5 over, oh wait, what did I do here? It was supposed to be a 5. I don't know what I was thinking there. So this becomes 2 times 3/2, and this is 1/5 divided by 3/5, which is times 5/3. And so that becomes 3 plus 1/3, so 10/3. So we were able to solve that one. We were able to solve A. It says, find each of the following if possible. If not possible, explain why. But we were able to manipulate those so that we could see what our R was and see what our A was. And once we were able to do that, we could use A over 1 minus R because they were both converging geometric series. And we did that and added them together and got 10/3 for A. Okay, so for part B, I want to decide, can I do something with this? And so I probably would go, well, let's go ahead and, since there's a monomial in the denominator, let's go ahead and split this up into 4 to the n over 5 to the n minus 7 to the n over 5 to the n. But I'm going to go ahead, when you can also, go ahead and split it up and put a summation on both of them. It doesn't matter. It's going to be, same thing. So when you see that, then you're thinking, ooh, okay, we've got summation n equals 0 to infinity. This is actually 4/5 to the n minus summation n equals 0 to infinity. This is actually 7/5 to the n. So the first one is a convergent geometric series with a sub 1 is 1 and your R is 4/5. Okay? But the second one, since your R is greater than 1 and is divergent, if one of them diverges, the whole thing diverges. Okay? So we're going to say, since this one diverges, because R equals 7/5, which is greater than 1, so the whole thing diverges because one of them does. Okay? Okay, so now that brings us to properties of infinite series. Given two convergent series, summation a sub n and summation b sub n, where a, b, and c are real numbers, if the summation of a sub n is a and the summation of b sub n is b, then the following series converge to the given sums. So you can see that it's almost like you can pull that constant c out times the summation value, right? Whenever on the second one, summation from n equals 1 to infinity of a sub n plus b sub n, if I knew what a sub n was and I knew what b sub n was convergent to, I could just add those two values. And again, on the third one, I could just subtract those two values if I knew what they were. Okay, so that's going to lead us to the telescoping series. Let's investigate a fun series where the terms collapse like an old-fashioned spyglass or telescope. This type of series is not used very often, but they are fun to consider. Example number 4. Use partial fractions and the limit as n goes to infinity of a sub n to find the sum of the series. So, what we're going to do on this one, summation n equals 1 to infinity of 1 over n times n plus 1. So what I want to do is I'm over to the side, I'm going to go, well, I know that I want this to be a over n plus b over n plus 1. That's what we do with partial fractions. We take a times the other denominator plus b times that other one's denominator and set it equal to whatever my numerator is there, okay? And then we say if n equals -1, then negative b equals 1 and b equals -1. If n equals 0, then a equals 1. So here's my a and my b. So that means that I can change that summation, summation from n equals 1 to infinity. I can change that summation n equals 1 to infinity, your 1 over n minus 1 over n plus 1. And so, again, since I'm summing those, I could change that into summation n equals 1 to infinity of 1 over n minus summation from 1 to infinity 1 over n plus 1. So I'm going to look at this would be 1 minus, and then this one would be, when I put a 1 in, 1/2, and then plus, I've got 1/2 for the first one, minus, and then when I put a 2 in here, I get 1/3, plus, and then I do the first one with 3, 1/3, minus, the next one would be 1/4, okay? So dot, 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 okay? So that's going to keep going until I get, I'm going to get a negative 1 over n, I'm going to get a positive 1 over n, and then I'm going to get a negative 1 over n plus 1 at the very end after I keep going. But notice that all of these are going to cancel. Like the negative 1/4, it'll have a positive 1/4 to cancel. Even this negative 1 over n and this positive 1 over n. The only two things that are not going to cancel on this one are going to be the 1 and the minus 1 over n plus 1. So you see how I have taken these and I've used partial fractions to kind of show me what is left on a telescoping series. Okay, so, you know, what they showed you here, 1 over 1 times 2 plus 1 over 2 times 3, you would not be able to see the collapsing until you looked at it in the way we just looked at it. So if I was going to look at the limit of the nth term, limit as n goes to infinity of this summation 1 over 1, or 1 minus 1 over n plus 1, I could see that this is going to have a limit because, of course, that second term is going to go to 0. So this limit is going to be 1. So that is going to be the sum of the series. Okay. So now, example number 5. Given the sequence a sub n equals 1 over n times n plus 1, explain the difference between the sequence a sub n and the series summation a sub n. So for this one, remember what we said about sequence. Sequence is not the summation, right? If we had sequence a sub n, that would look like this. 1/2, comma, because when I make that n equals 1, I get 1/2. When I make it n equals 2, I'm going to get 1/6. When I make it n equals 3, I'm going to get 1/12. Okay, so that's what your sequence looks like. And can you see, oops, that these values are just going to keep staying 1 in the numerator, and they're going to keep getting larger and larger and larger in the denominator. So this one converges to 0. The limit as n goes to infinity of a sub n would be 0 here. The series summation n equals 1 to infinity of 1 over n times n plus 1 would be 1/2 plus 1/6 plus 1/12 plus ... And this one, when you add them up, we said that the sum is equal to 1. So for this one, that's the difference between this sequence and this series. We just showed you how that sum was going to give you 1. We split it up using your partial fractions and saw that that was going to sum to that, and we took the limit as n goes to infinity, and we got that sum to be 1. Okay, example number 6. Write a geometric series for the repeating decimal 0.05 repeating as the ratio of 2 integers. This is very, very interesting. If you had that number, it would be 0.5, 0.5, 0.5, 0.5, ... Okay? And so let's think about what that would look like. Because I know that this first one is 5/100ths, okay? Which another way to write that would be 5 over 10 to the 2. But then I could add 5/10,000ths, 5 over 10 to the 4th, and then ... right? So the next one would be 10 to the 6th in the denominator, and then 10 to the 8th in the denominator. For this one, your first term is 5 over 10 to the 2nd. Your r, because every time, what are you multiplying by to get to the next term? You would be multiplying by 1 over 10 to the 2nd to get the next term. So if you wanted to, you could think of this as the summation from n equals 0 to infinity of 5 over 10 to the 2nd times 1 over 10 to the 2nd taken to the nth power. So if I started at 0, that first one wouldn't count, so that would give me my first term, 5 over 10 to the 2. And then my second term, my n would be 1. So you see how sometimes we use n equals 1 to infinity, sometimes we use n equals 0 to infinity. We used n equals 0 on this one. So once I see that, and I can see that my r is between 0 and 1, so it therefore converges, and I can say that the sum, which would be basically that, is going to be equivalent to a over 1 minus r, with our first a being 5 over 10 to the 2nd, 1 minus 1 over 10 to the 2nd. So this would be 5 over 10 to the 2nd times, this is going to be 99 over 10 to the 2nd, which would be 10 to the second over 99 that I'm multiplying by. My 10 to the seconds are going to cancel, and this 0.0505 repeating is equivalent to 5/99. That is the ratio of two integers. If I put 5 divided by 99 into my calculator, I would get 0.05 repeating. Okay, this leads us to our nth